guys, if you want to watch this too, you can. I don't know if you care to, but okay. Yep. Multiply everything by 2x plus 3, 2x minus 3. Yep.
Actually, you just go ahead. I got so lost on each.
Oh, okay. Well, let's go with more of these rational polynomial expressions. So we had the y equaled 5 over x minus 4. Was our first example? Okay. So now when we're graphing these, the vertical asymptote is where I always start because it's just your NPV, right? So I can say x minus 4 cannot equal 0. So x cannot equal 4. So there's our vertical asymptote. Well, horizontal asymptote, well, square that off. The horizontal asymptote, we use those three rules. Is the p of x have a less than, equal to, or greater than? It's less than because the degree of the 5, well, it's 5x to the 0 really, because it's not there, and then x to the 1. So it's actually greater in the denominator, right? So it's less than, so I know y cannot equal 0. Pretty straightforward, okay? So when I go and I plot this now, if I draw a coordinate plane, I'm going to use a different color here. At x equals 4, 1, 2, 3, 4, I have a vertical line that the graph will never cross. And I also have a horizontal line at y equals 0, so right along the axis, isn't it? All the way like so, that our graph can never cross. Pretty straightforward. Well, now, just a matter of doing a little table of values. Fun. So, let's do that. I'll come in here, right here. X, Y. Something like that. We've got these 4 new areas of the graph that the graph's going to cross in, right? Or go in. So when I pick some numbers to plug into the original equation for x, I'm looking at ones that are going to make it the division nice and easy. So when I think of numbers that can go in for x, I know 5 would make a nice number. I also know something like -1 would make a nice number. You know, just by looking at the question, right? So when I do that, let's just do those two numbers real quick. If I plug in 5 for x, I get 5 minus 4 on the bottom. So 5 divided by 1 is 5. And if I did -1, and -1 minus 4 is -5, so 5 divided by -5 is -1. So when I come over to this graph here and I plot these, I got 3, 4, 5. And I go up 1, 2, 3, 4, 5. So there's 1 point. The second point we found was -1, -1. So that's -1, -1. So it's somewhere in here. So I already know, because of the asymptotes, you know how they act like boundaries, like we learned before? I know that this graph's going to try and get as close to that asymptote and as close to this horizontal asymptote as possible. So I can go and check some other points. If we wanted to, 9's another good x value to plug in. If I plugged in 9, 9 minus 4 is 5. So 5 divided by 5 is 1. So if I went all the way over here, 6, 7, 8, 9, and up 1, you can see what's going to happen. So this kind of goes back to those hyperbolas and stuff we did, eh? Like so. And like so. And in this one, again, a number like 3 might be a good one to plug in to our table of values to see, to get it more accurate, right? We don't have to do all of them, but we want to get the general shape. So when I plug a 3 in, I get -1 downstairs. 5 divided by a -1 is -5. So over at 3, I go down 1, 2, 3, 4, 5. So again, we got some crazy doohickey like so. And I mean, I can get it more accurate by getting a y-intercept, by plugging 0 in for x and stuff like that, which would be -1/4, -1 1/4. So yeah, right in there. I mean, we're close with our graph, right? There's our graph. Okay, so let's try another one. So I guess if we were to write steps, they would say find your vertical and horizontal asymptote, find maybe your y and x intercept if you have them, do a table of values and just draw it, right? Let's do another simple one just to kind of keep us going here. Y equals 3 over x squared plus 1. Now these ones are kind of neat. And you'll see, actually, I jumped the gun here because I actually put the graphing reciprocal functions in the next unit, and that's all this stuff is, only we kind of mess around with them a bit, take it a little farther than we have to. Well, vertical asymptote is where the denominator can't equal 0. Can we factor that denominator? So there is none. There is no vertical asymptote. No horizontal asymptote. We think of the rules in this one. 0 again, right? Because the denominator, or the polynomial up top is less degree than the bottom, so 0. Plot them. And the only one we've got is that horizontal asymptote is 0. And I go along. Done. Okay. So now, all we know is the graph cannot cross the x-axis. So, here we go. Table of values, x, y. This is kind of an ugly one, actually. And we'll only do the table of values now until we learn what we do in next unit. So it's kind of like I teach you all the ugly stuff and then I show you all the shortcuts. So if I plug a 0 in for x, this is going to give us our y-intercept, but it's also going to give us what for a value of y? 3, right? Because 0 squared, 0 plus 1. So 0, I go up 1, 2, 3. And I plot that. Is there anything else that's going to be work out real nice for values of x to plug in? No. You think about it, everything we plug in here, negative or positive, it's going to get bigger and bigger and bigger, right? That x squared. So if we plugged in a 1, 2, 3, 4, it's just going to keep getting bigger down here. So what's going to happen to our y value? Smaller. So as x gets bigger and bigger, our y value is getting smaller and smaller. Always positive though. And this way as well. That's kind of like your first introduction to limits. So when you get to grade 12 calculus, that's exactly the kind of question you'll talk about. You'll say, okay, as x is getting bigger, or x approaches infinity, what happens to your function? Well, it gets smaller and smaller. So I know, let's just go plug in, 1 and negative 1, just to show you. Well, if I plug in 1, I get 1.5 and 1.5, right? Because it'll be 3 halves. So over at 1, I get 1.5 and 1.5. So what's going to happen to this graph? Yeah, exactly. It's going to keep going down like this, and it's going to keep going down like this. Because it's going to try and get close to 0 as possible, but it never hits 0, right? So that's about the weirdest kind of question you get. So I always recommend doing at least 3 points. And when you don't have a vertical asymptote, you want to make sure what's going on. Okay, we'll do one more example, and then I think you'll have enough, because this last example's kind of the extreme that you'll get. You can see it already, eh? So y equals 2 over x squared minus 9. And here's a little hint. When you've got x-intercepts, or no x-intercepts, you're always going to have that weird looking graph, like we just did. So this one's going to be sort of normal. Okay, get to it. Vertical asymptote and horizontal asymptote. So our vertical asymptote, 3 and negative 3. Yeah, we just factored the bottom. So 3, negative 3. And the horizontal asymptote, 0 again. it's very rare that I'm going to give you one that's moved, but you got to know that it could be somewhere else, okay? And you'll see it. So let's go and plot those at least. So at x is 3, whoops, so I can make that a bit bigger. X is 1, 2, 3. And 1, 2, 3, negative 3. All the way down. And a horizontal asymptote of 0. So going across the x-axis. Okay, just to kind of show it. Whoops. Under your feet there. Okay. And then pick some values for a table of values. Now I've got a bunch of regions here, okay, that we got to test. So that's kind of how I look at it, as regions. So I got on the left-hand side of the asymptote, I got the middle part, and I got the right-hand side. Okay, so all these are kind of what in calculus you'll end up referring to as like critical points or critical values and stuff. Because everything in calculus is about graphing. That's why I would say grade 11 is the preempt to it. So let's just plug 0 in. If we plug a 0 in for x, we get 2 over negative 9, right? So negative 2 ninths. And I don't care what the decimal is, but all I know is it's really small negatively. So right there. Okay? So you can guess what this graph's going to do because we've discovered that all of the graphs seem to follow the boundaries, right? So I'm going to test some other points here, like maybe 2. When I plug a 2 in, I get 4, and I guess negative 2. So positive 4. So 2 over negative 5, so negative 2/5, and negative 2/5. So not quite as small negatively, but still, we're down like so, and down like so. Like kind of like at a half, I guess. So this graph, I'm betting, as closer and closer we get, it's going to keep trying to approach that. It's going to keep trying to hit 2, right? Now, we got to check out in these regions. So again, I don't care what numbers we pick, but we got to find something. So let's go and try, I guess, a 4. Yeah, try a 4. And I mean, it's going to be the same for a negative 4, right? Because we're squaring it. So when I plug a 4 into x, I get 16. 16 minus 9. 7, so 2 over 7. So it's positive really small, right? So positive really, really small. And positive really, really small over here. And I mean, we can get closer and closer to 3, but never touch, right? So you think about it, if we put 3.0000001 in here, okay, it would be 9.00000 something, right? Squared. And that's almost 0, but not quite. It's like 0.0001 if we subtract the 9. So it'd be 2 divided by really, really small. Well, that's going to be really, really big, right? Way up here. So I know that this graph is going to come like this and is going to follow out like that. Okay? And I mean, there's no sense going and doing a silly table of values, especially if you know that that's the shape it's going to end up being. I mean, we can keep plugging in number. If you went and plugged in 5, it's going to be even smaller. And 6, it's going to be even smaller. And 7 and 8, right? It's going to keep trying to get to 0, but it'll never get there. And same with this way. As we get closer to 3, it's going to keep getting bigger and bigger and bigger and bigger and bigger and try and get there, but it'll never get there. That's what the asymptotes do. So that's limits, sort of, from grade 12 calculus. And that's as hard as it gets.